I designed this presentation to be understandable also for undergraduate students, and I thank the few undergraduate students to be here. My plan is to present somehow two separate items. In the first part, I intend to give rigorous proofs of the Herglotz theorems, and that would be as rigorous as possible in order to be understandable. In the second part, I have in mind to present two main applications. One is one of the famous theorem of Caratheodory, Constantin Caratheodory, and the other, if time permits, will be in getting the spectral theorem for definitizable self-adjoint operators on Krein spaces, which is one of the main applications of the Herglotz theorem for holomorphic functions. So, as we know, and our students learn in our department, mathematics is the only human activity that does not need to change the facts established previously. But we have to pay a high price for this, because mathematics is not directly related to reality. And if we want to relate it, we have to make big efforts in order to get mathematical models and work with them. In this talk, I want to emphasize these ideas by presenting some mathematical facts that have been established more than 100 years ago, but prove to be extraordinarily efficient in current research. So I will start by giving some motivation, which is coming from applications. As we see in courses on ordinary differential equations, if you consider a second-order linear differential equation operator, the classical theory works wonderful if you assume that the coefficient function P of x is strictly positive. Then you are getting the so-called stationary Schrödinger operator, which has extraordinary applications in mechanics or in quantum mechanics. Now, there are situations in which the weight function P may change sign. Some applications are requiring this. And in this case, the classical theory doesn't work. And I made a search on MathSciNet a couple of days before, for exactly for these words, indefinite Sturm-Liouville differential operators. And I made a search with these words on MathSciNet for the interval 2000 to 2018. And I got 48 articles devoted to it. So that means an average of 6 articles per year in extraordinary, very good journals. So this is a very active research area. Now, assuming that P does not vanish almost everywhere and letting R to be the inverse, what is the novelty of this approach is that we are considering the weighted Hilbert space L2 with the absolute value of R, but on which we have an inner product which has a weight R, which is indefinite. And this already puts us in a different realm. So we are working in a space having an inner product which is not positive semi-definite, and the theory is completely different. So in this case, the domain of L is not a bounded operator, it's an unbounded operator. And the best thing that you can get from the spectral theory is to get a kind of symmetry by making L self-adjoint with respect to this inner product. Okay, now there is a big trouble with the domain of L, which only we mathematicians are caring about. In physics, they don't do it too much. In our case, we consider the domain of L to be all the functions in L2 with weight the absolute value of R, for which both f and f prime are locally absolutely continuous, and L of f is in L2. So under certain special conditions on the weights, we can hope to get L self-adjoint in such indefinite inner product space. But here is a big trouble, because the spectral theory of self-adjoint operators in indefinite inner product spaces is very bad. So there is no way to hope for a spectral measure for this. And the best thing that you can get is a kind of spectral distribution which may have not so many singularities, so you are completely in a different world. But if time permits, I will come back to this at the end of my talk. Okay, so now I have to indicate the sources. So here are the classical sources. The original paper of Herglotz in 1911, and the original paper of Caratheodory in 1907. Caratheodory had a different proof. He was an extraordinary mathematician and very creative. But by means of the Herglotz theorem, we can get a very simple proof of Caratheodory theorem. Now I indicate this book from 1991, in which they collected a lot of classical papers. Herglotz, Schur, Pick, Nevanlina, Hermann Weil.
You mean joint paper?
No. Okay. They collected the papers and they made them available, because otherwise it's very difficult to find them. Okay, now my presentation, of course, it uses modern sources. So I will make a proof of the Herglotz theorem following the book of Paul Kouzis from 1998. Is the second edition. The construction of the spectral function was done by Langer in his Habilitationsschrift from 65, but it was never published until 1982. But the most of the material I'm presenting in my talk are actually taken from a book I have in preparation. And every year I'm writing in my annual faculty survey that this year I hope to finish the book.
For how many years? Can you just say that?
Well, it's more than 10 years. Yeah, unfortunately, I hope it will be not that like that. Okay. So I'm starting with basic things that students learn in the courses of complex analysis with Poisson kernel. Poisson kernel is positive. It can be extended by having periodicity 2 pi with respect to the second argument phi. And actually it comes from a power series expansion indexed on integer numbers, which is, of course, converging on compact subsets in the open unit disk. Now, integration term by term gives us that if you integrate it from 0 to 2 pi, you are getting exactly this constant. We are going to use it a lot. Now, as we learn in the course of harmonic analysis, and probably a little bit in the calculus course, a real valued function defined in some open subset of the complex plane is harmonic if it's at least 2 times differentiable and it's a solution of the Laplace equation. We know that if it's a solution of the Laplace equation and at least 2 times differentiable, then it will be indefinitely differentiable, so it is of class infinity. Now, for the moment, we consider a harmonic function which has this property in a little bit larger set than the closed unit disk. So I will make some pictures in order to have some ideas what we are doing. So here we have the unit disk in the complex plane, and for the moment, assume that we have harmonicity in a little bit larger set. Then, in this case, we have the Poisson integral representation of the function for each r between 0 and 1 with respect to the Poisson kernel, and using the value of the function on the unit cycle, which is in the domain of harmonicity. Of course, by integrating the function on each cycle of radius r, we are getting exactly the constant u of 0 times 2 pi, as we know. And this is the first theorem that we are going to get. So the question is this. Assume that the function u is harmonic only in the open unit disk. How much can we get a Poisson representation formula for the function inside the open unit disk with respect to the Poisson kernel and some values on the boundaries? Now, it seems that if we want such a thing, then some control on the growth of the function are necessary. This is a case I need. So if all these averages are upper bounded, so this supremum is finite, then we can always get a finite signed measure mu on the interval 0 to pi, such that we have the Poisson representation of the function u on the unit cycle, but with respect to the measure, not a function here. Okay. Now, what about having a function on the boundary? Okay, for this we have to change the type of boundedness. If p is strictly larger than 1 and finite, then we can have a Poisson representation with respect to a function on the boundary if the function is supposed to be in LP, if and only if this boundedness condition holds. Yeah? For the case p equals infinity, we are looking exactly for uniformly bounded functions in the open unit disk.
So now this measure is absolutely continuous?
Yes, in these cases, we are getting absolutely continuous measures, and the functions are in special LP spaces. Now, these two parts, B and C, are not our concern, so what we are going to talk is about this case. Okay, the proof that, the modern proof that can be seen in some of the textbook is following a duality argument. So we consider these functions un, we are making this scaling here. So actually, we are getting functions which are holomorphic in a neighborhood of the closed unit disk in this case. And of course, for this kind of functions, we have the classical Poisson representation with the value of the functions on the boundary. And now we are interpreting this actually as measures. Yeah, we are putting these weights, this distribution function un of theta, and then we are using an argument from functional analysis that the Banach space of continuous functions on the compact interval 0 to pi with the sup norm has a dual, the Banach space of finite signed measures on 0 to pi with this norm. Here we have the absolute part of the measure. Since our measure is finite and signed, it is by Jordan's theorem the difference of two positive measures, and then we are taking the sum of it, and we are getting this measure with respect to which we are defining this norm.
You mean the total variation?
Yes, the total variation, but actually we are interpreting it with respect to a certain measure, yeah? You're right, it's a total variation. Okay, anyhow, by our boundedness condition, this suprema is finite, yeah? Exactly because of this inequality from here. Hence, we are using a classical theorem in functional analysis that bounded subspace in Banach spaces which are duals of our Banach spaces are W star precompact. Hence, we can get a subsequence which is W star converging to a measure mu. And this is how we are getting the measure mu. Yeah? It's a duality argument. Explicitly, this means the following, that for any function continuous on 0 to pi, this limit, it is exactly the limit of the function f with respect to the measure mu. Of course, now we have the Poisson representation for every function u and j. And the Poisson kernel, considered as a function in one variable, is continuous, of course. So we can use this limit from here. And then by passing to the limit, we can obtain exactly the required representation, Poisson representation formula for the function u inside the open unit disk in terms of the Poisson kernel and the measure mu. This is one implication in the theorem. For the converse implication, we have two things to prove: the harmonicity of the function and the boundedness of the averages. Yeah. Okay. For harmonicity, we have at least two ways. One is a hard way. So we can use derivation with respect to r and theta, and then use a Poisson with a Laplace operator in polar coordinates. Or the easy way, we are using the power series expansion of the Poisson kernel in order to obtain the values exactly as the sum of this integral, and we have the convergence of it, and this is sufficient in order to get the harmonicity in view of the relation with holomorphic functions. Yeah, we can produce holomorphic functions which have the real part exactly the function u. Okay, now for the boundedness part. For the boundedness part, we observe the following, that we can write the absolute value of the function u as the product of a function gr in L infinity of norm 1 and the function itself. And if we're integrating the absolute value of u, and then we are using exactly this representation, we can use now the representation of the function u of r e of I theta by the classical Poisson representation, by the representation, sorry, that we have with respect to the measure. And then we can make this inequality. Okay, here the Poisson kernel is positive. This is not positive, but everything is positive. So we can measurize exactly in this way. And here it appears the absolute value of the measure mu. And of course, what we have inside equals 1, because we are integrating the Poisson kernel on the cycle. And we are getting a fixed number, and this is not depending on r, so we have the boundedness property as we want it. Okay. Now, this is not exactly the mathematics that was done 100 years ago. So if we want to go into those terms...
But I'm sorry, did he use here the selection principle 100 years ago?
Yes, he was using a selection, but actually it's not needed, the selection. Yes, you can use a Cantor diagonalization argument. Yes, yeah. In order to escape this W star compactness thing. Okay, so now do we want to put it in more the beginning of the 20th century mathematics? So if we have a measure on 0 to pi, a signed measure on 0 to pi, we can consider the function which is integrating from 0 to t the measure. This function has bounded variation. And then we can interpret this Poisson representation with respect to the measure as a Stieltjes integral, which existed at that time. So Stieltjes integral existed at that time. So actually, that was how they were doing with this kind of integrals 100 years ago. So, and this is what we are going to do, because we are going to need this interpretation. So instead of seeing this as an integration with respect to the measure mu, we can use it as we can see it as a Stieltjes integral with respect to the function mu of bounded variation. Okay.
using the same notation with
Sorry?
you're using the same notation for the function
Yes.
and the measure and
You're right. You are perfectly right. You're perfectly right. Yes. Okay. So the first Herglotz theorem says the following: that if we have a function which is harmonic and also positive in the open unit disk, this is happening if and only if there is a non-decreasing function mu on 0 to pi, such that it has the Poisson representation with respect to the function mu inside the open unit disk. And in addition, which is somehow clear from what I explained in the previous page, mu can be obtained in such a way that it is left continuous and normalized by mu of 0 equals 0, and in this case it is uniquely determined by the harmonic function u. Okay, so the difficult part of this theorem we are getting in modern terms from the previous theorem. Why is this? So what is novelty here is that we have only harmonicity of the function and positivity. So we are actually getting rid of that boundedness condition. And what we have to do is we have to relate the boundedness condition with this positivity condition. So if u is a positive harmonic function in D, then by using the mean integral formula for harmonic functions, for any r larger or equal than 0 and strictly less than 1, we are getting that the integral of the absolute value is the same with the integral of the function, and we are getting a constant. So we are having the boundedness, that boundedness condition, for free, exactly because the absolute value is the same with the function. So it's a positivity. Now, the only thing that we have to make sure is why we get our measure or our function to be non-decreasing in our case. Yeah, the function should be non-decreasing in order to get a measure which is positive. We have to go back a little bit to the proof of the theorem. We got that measure by a subsequence u and j, and we can show that. I mean, since all the functions u sub and j are positive, everything we have here in the integral, if g is a positive function continuous on 0 to pi, is positive, and we are getting this integral of the function g with respect to mu as a limit of non-negative functions, and this is of course non-negative. And this is sufficient in order to get that the measure is positive, and hence the corresponding function is non-decreasing. Yeah? Conversely, we are using exactly the theorem that we have proven, and we get the result. Okay, now the second Herglotz theorem, which is referring to complex functions. This theorem is saying the following: a complex function f is holomorphic in the open unit disk, and it has non-negative real part, if and only if it has this representation with respect to some non-decreasing function on 0 to pi and some constant, some real constant beta.
With analytic extension?
This is analytical extension, and we are replacing the Poisson kernel with this kernel because this kernel has the real part exactly the Poisson kernel, and the imaginary part is the so-called conjugate Poisson kernel. Yeah? So by doing this, and the knowledge that we know from complex analysis that the interplay between holomorphic functions and harmonic functions as the real and the imaginary part, by using the conjugate, the so-called conjugate part of the harmonic part, we are getting exactly this formula and, of course, the representation.
Normalize somehow this imaginary part since up to constant.
Yeah, actually, we are normalizing it by requiring to be 0 at 0, you see? And in this case, you have uniqueness. Otherwise, you're right, it's up to an additive constant. Yes. Okay. Now, I want to go into the applications. And the first application will be for Caratheodory theorem. In order to explain Caratheodory theorem, I have to go a little bit into kernels, and especially positive semi-definite kernels. So for the moment, we are interested only in kernels which are defined on integer numbers. So a kernel in mathematics has different meanings, but in our case, it will be a function of two variables, complex valued. And in our case, it will be a function of two integer variables. And the kernel case called positive semi-definite if for any integer numbers m strictly less than n and any complex number lambda m through lambda n, we have this double sum to be non-negative. Now I have to explain a little bit this business with kernels in the case of integer numbers. So what we are doing, we are taking this lattice made up with integer numbers. But of course, I want to make a little bit of abuse, and since otherwise we have to look at the picture in a different way, I will change this sign in this direction. And I will explain why we are doing this. Yeah, for every mn point in the lattice, we have a complex number k of mn, which is given, yeah? So imagine the lattice in the plane, and at each node, we have a complex number. What is actually this semi-definite positivity? It's the following. Okay, now since I have this, the main diagonal is here. This is what I wanted. And then you are taking any square matrix which has the diagonal exactly on the main diagonal of the lattice. Yeah? You can take it as large as you want. It should be squared, and it should keep this diagonal on this side. And you want that all these matrices to be positive semi-definite, because this is exactly the positive semi-definiteness for matrices. But of course, there is no boundedness condition on the kernel, so I cannot make an infinite matrix from here. It's just a kernel, yeah? There are only points. But positive semi-definiteness is very strong condition. So, any positive semi-definite kernel is Hermitian in this sense, yeah? Like a matrix. It's exactly like a matrix. What we have here is exactly the complex conjugate of what we have for the symmetric one.
You have to move one more step.
Ah, sorry. Yeah. Thank you. You have a you have a broader perspective, which is important. Thank you. Okay. So any positive semi-definite kernel is Hermitian in this meaning. But we are interested in special kernels, the so-called Toeplitz kernels. And these Toeplitz kernels have the following property, that what we have here actually depends only on this, you see? So on this parallel with the main diagonal, we have constant values. On each straight line which is parallel to the main diagonal, we have constant values, yeah? This is this property from here. But that means the following, that actually we need only one sequence in order to parameterize Toeplitz kernels. So k of mn actually depends only on the difference of the two indices m and m. So k of mn is a subindex m minus n, where an is a sequence indexed on integer numbers. In the case of Toeplitz kernels, positive semi-definiteness can be written much nicely. So it is, so here is 0, 0. So because of that, you only need, it's sufficient to have these matrices, these square matrices from here, so going downwards, yeah, downwards and on the right. You don't need to go upwards. So that's why actually positive semi-definites for Toeplitz kernels can be written in this way, yeah. It's equivalent with this inequality for any complex numbers. And here is Caratheodory theorem. So Caratheodory was an extraordinary mathematician, and it was just at the beginning of this, what is called geometric function theory. And he was interested, and they were interested actually at that time, in giving characterization of different conditions of holomorphic functions in the open unit disk in terms of the Taylor-Maclaurin coefficients. And what he found, but by a completely different method, was exactly this theorem. So if f is a function holomorphic in the open unit disk, normalized at 0 by giving the constant 1, and having the Taylor representation in the open unit disk, let us consider the Toeplitz kernel, which is defined by the sequence of the coefficients. And we need to define A0 equals 2. It comes from the calculations. A0 must be 2. And we have also to define A with negative index. And because we want something Hermitian, we define A minus M to be exactly the complex conjugate of AM for all M larger or equal than 1. And then the result is that the real part of the function f is non-negative in the unit, in the open unit disk, if and only if the Toeplitz kernel T is positive semi-definite. And the theorem, and this theorem, as I said, originally has a completely different proof, very ingenious. The proof that we are going to present actually was done by Otto Toeplitz after seeing Herglotz's theorem. Okay, so we have two implications. One implication is easy. Consider the Toeplitz kernel T on the integers, defined Tmn equals a m minus n, a02, and Hermitian, and take lambda 0 equals 1, lambda 1 equals z, lambda n, z to the power n, and so on, infinite, for any z in the disk. Then this double series, double infinite series, can be calculated, and it is exactly 2 times 1 minus the square of the absolute value of z at minus 1 times the real part of the function f. Now, we have a little bit of trouble with convergence of this double series, but there's not a serious problem. Why? Because we know that inside of the open unit disk, the Taylor series converges actually absolutely. And there is no problem in changing the order of summation. So there is no problem on that. And there is also no problem of convergence because the Taylor series converges uniformly on any compact sets. Okay, here what you have to do in order to get this formula is to get a power series representation of 1 minus the square of the absolute value. But this is okay because we know that it has a very simple, it's a geometric power series, yeah? And then the real of f of z, of course, has a power series expansion in terms of the z and z bar. So actually what we have to do...
I missed somehow. What are these lambda maxima? Can you repeat?
Sorry?
Lambda. What are these lambda I missed somehow?
In the definition, they are just arbitrary complex number. So this is happening, this inequality must happen for any n tuple, n plus 1 tuple of complex numbers. Yes. So he's making this choice, but you see here he has an infinite sequence. But the thing is the following. Once you have this formula, by the positive semi-definiteness, this is non-negative because it's the limit of something non-negative. Yeah? You play a little bit with the remainder in the Taylor representation. and you are getting it. And from here, since this coefficient is non-negative, actually it's strictly positive, the real part of f must be positive. Okay. So we have one implication, the easy one. The difficult one, we are using the canon of the Herglotz theorem. We have a saying in mathematics, never kill a sparrow with a cannon. But in this case, okay, so Herglotz theorem is a cannon in one way, but Caratheodory theorem is not a sparrow. It's also another big wall. So, assuming that the real part of the function f is non-negative, we have Herglotz theorem, we have the integral representation of f with respect to this kernel. Normally we have this imaginary part from here. We actually have some imaginary part from the integral because we don't have reality here. This kernel is complex valued. But we can get rid of this beta by the normalizing condition f of 0 equals 1. So beta is 0. And then we can calculate in a straightforward manner the coefficients as integrals of this e to the power minus int. And then we can write for any n plus 1 tuples lambda 0 lambda n, we can write this double sum as the integral of the square of the absolute value of this sum with respect to rho. But rho is a non-decreasing function, so everything here is non-negative, yeah? So we have this integral non-negative, so we have this non-negative. And then Caratheodory theorem is proven. Now, I want to make a digression here, because, okay, first let me go back in this formula. So this formula is important. Why? Because somehow it relates the function f directly to the kernel, to the Toeplitz kernel. Okay, now our kernel, it's defined on integer numbers. But there is a general theory of holomorphic kernels. And actually, this construction is the origin of what is now called as a Caratheodory kernel. So if you have a function holomorphic in the open unit disk, then you can write the Caratheodory kernel in this way. So this is f of z plus the conjugate of f of zeta divided by 1 minus z zeta bar. If you make z equals zeta, you are getting exactly that formula with a constant, with a multiplicative constant. It's not exactly this. Why? Because here we don't have the real part. It's only, we need the coefficient 2 for this. But anyhow, for z equals zeta, we are getting exactly that formula. And now we are going in a different realm. We are going into kernels which are defined on domains in the complex plane. They are complex valued. But that definition of positive semi-definite still makes sense. Why? Because we only take positive, we are getting only a finite number of elements, we are making summations. So the thing is that under certain conditions, these Caratheodory kernels, they become positive semi-definite. And then it's a huge business out of this. Our colleague Turgai Kaptanoglu is specialist in the multidimensional case. But out of the Caratheodory kernel, there are two others which are equally important. One is a Nevanlina kernel, which is defined in the upper half plane of the complex plane. And the other is the Schur kernel, which is defined in the open unit disk. Now, the interest for the Schur kernel is when the function theta is uniformly bounded by 1. So it has values, it maps the unit disk into the unit disk. And then this kernel is becoming positive semi-definite. And then we have integral representations and a lot of business. I want to point out that this holomorphic kernels are extremely useful in engineering problems. Why? Because in electronic engineering, despite our prejudices, then in applied mathematics, they only use real numbers. This is not the case. By the way, there is no way to build a transistor without complex functions. There is simply no way. Why? Because they model different kind of electronic devices by so-called transfer functions. And transfer functions are functions in the complex plane. And it is exactly the behavior of certain kernels which gives certain properties of the transfer functions. And there are questions which are very important in interpolation theory. You are giving a finite number of points, you are giving some certain numbers, and you want a function with certain properties to take exactly those values at the given numbers. This is what we call complex interpolation theory. And they are exactly using this kind of kernels. Okay, but this is just the information. I think that this topic deserves a series of talks, not only one talk. Okay, now I'm coming to the problem that I started with. I want to show how we can use Herglotz theorem, actually how was used Herglotz theorem for getting the spectral theorem for a certain class of self-adjoint operators in indefinite inner product spaces. So I'm starting with some terminology. Assume that X is a complex vector space. What we call an inner product is exactly a complex function on two variables on the complex vector space X, which is linear in the first variable and conjugate symmetric. We don't assume any positive definiteness. And that's why we call this indefinite inner products. Okay, now there is a theorem which is telling us under which condition we can have a reasonable operator theory in this kind of spaces. So assume that H is an indefinite inner product space. We have three characterizations. The first one is geometric. The second one is operator theory. The third one is topological construction, characterization. So the geometric construction says that H can be decomposed into a direct sum of two subspaces on which, on H plus, this inner product becomes positive and a Hilbert space, and the negative of this inner product becomes a Hilbert space on H minus. The second characterization tells that there exists a linear operator on H such that it is an idempotent, J square is 1, X, and such that the indefinite inner product is given in terms of a Hilbert space inner product. The third characterization is topological. This condition is saying that this norm is self-dual. Once you have an inner product, you can define the dual of a norm with respect to it, and the norm must be self-dual. Now, a space having any of this equivalent characterization is called a Krein space. But there is a nice story here. Actually, Krein was not, Mark Krein was not the first to deal with these spaces. The first one who did in a systematic way was a Finnish mathematician, Rolf Nevanlinna, and he had a series of papers in which he investigated these things. Actually, these spaces appeared before at Pontryagin, but Pontryagin considered the case when one of the components has dimension finite. And this is what we call today a Pontryagin space. But the story is even nicer. The first one who considered these spaces indefinite inner product spaces was Sobolev. And Sobolev paper was never published. And I can tell you from my Russian colleagues why it was never published. Because that paper was dealing with a mathematical model of an object which is filled with a liquid and is moving. And you can imagine what kind of object is moving and is filled with a liquid. It's a racket. So that paper was never published.
So what?
It's a racket.
And this is Sobolev, which Sobolev space is just famous Sobolev.
A racket. A racket. A missile. A flying missile. So it was never published. A secret.
Even now.
Well, now it doesn't make too much sense because it's too late.
So, do we assume that it's complete in some of the...
In this case, it is complete with respect. Yeah, I'm talking about Hilbert spaces, you know?
No, the space H, the indefinite inner product.
Completeness with respect to what?
Yeah,
We don't have any topology on
what's
it.
the topology?
Okay, we have a weak topology, but this is not good enough.
And you saw reasonable theory in the sense of existence of some spectral results or what?
Exactly what I'm trying to explain to you now. Okay, so in Klein spaces, linear operators can be associated to adjoint operators. It is pretty much as we do in the Hilbert spaces, yeah? We are working with unbounded operators, so they are defined on some subspaces. Most of the time, they have to be dense. The operator, we want it to be closed. And the domain of the adjoint is pretty much as we define it in the Hilbert space case. So there are all the vectors in K2 with the property that for some z in K1 and all x in the domain of T, we have Txy is xz. And then we just let T sharp y equals z, and we make the adjoint. And of course, once you have an adjoint, we have the concept of self-adjoint operator, so T equals its adjoint. But the spectral theory of self-adjoint operators in Klein spaces is horrible. So what is happening actually in these spaces is this. So we have the complex plane here. And you are looking for the spectrum. And the only thing that you can prove about the spectrum, it is symmetric with respect to the real line.
So it's not real.
No, it can have residual part, it can have a lot of non-real part.
In spite of self-adjoint.
In spite of self-adjointness, and because it is indefinite. Yeah? This is a trouble. The big trouble is indefiniteness. So, Heinz Langer, a German mathematician, wanted to have some conditions under which he can have a kind of spectral measure. And the first condition historically that appeared is a so-called self-adjoint definitizable operator, which means the following. First, you have to make sure that the resolvent set is non-empty. This is non-trivial. There are a lot of self-adjoint operators in Klein spaces that have trivial empty resolvent. No point where lambda I minus t is invertible. So first, the resolvent set must be non-empty, and there exists a non-trivial real polynomial p such that when you calculate p of a, this is just simple functional calculus, you replace lambda with the operator a, you are getting an operator which has a positivity condition on the domain of the power a to the power n. Now, there is a classical theory which can be seen in Danforth and Schwarz. The fact that the resolvent set is non-empty and the operator is closed makes the domain of any power to be dense. So it is sufficiently rich. Okay. And then a polynomial like this is called definitizing. Here is a little bit of notation. So z of p denotes the set of the roots of p. K of lambda is a multiplicity as a root. And then this new sub A of lambda is the so-called Riesz index. You see, these kernels, when you are making n larger and larger, they become larger and larger. So n is a first nature number at which they stabilize, if they stabilize. And then we denote by sigma tilde the extended the spectrum. That means if t is unbounded, we are adding the point infinity. And what Langer did, he made a little bit of construction. So if p is the definitized polynomial, he's choosing lambda 0, not real, but in the resolvent, and he's making this rational function, which actually is very good because it is bounded, actually it's null at infinity. N is a degree of the polynomial p. So Q of A is a bounded operator. It is still set-fold joint. And Q of A has still this positivity condition from here. And the first thing that he got, and this was a crucial point, was this theorem. So A is a self-adjoint definitizable operator with a notation from before. We can always find an operator-valued function defined on the real line with values bounded operators with these properties. So the important fact is that we have an integral representation of the resolvent function with respect to this function that we are taking the, so this is a kind of vector-valued Stieltjes integral.
And who is the author of the theory?
Heinz Langer. It was in his Habilitationsschrift in 65, but it was published only in 82. So this is an important fact, this integral representation. Now, how he used Herglotz theorem was a very clever thing.
What's L of K once more?
Bounded operators on K. Bounded linear operators on K. B of K.
Bounded with respect to what?
Sorry? K is a Krein space.
Yes.
Krein space has an Hilbert inner structure.
So with respect to that.
Yes. Everything is that. But it's not unique. There are many Hilbert structures which are equivalent, but the topology is unique, but not the norm.
For boundedness is the same.
Yes, but boundedness is the same, yeah. Okay. So the idea is to define this function with a function small q to get this integral, this representation of the resolvent with respect to this function q, and then for each x to define this function. So fx of zeta, for zeta in the resolvent set of A, is exactly this. Q of A is bounded operator, the resolvent is bounded, and this number from here, whenever zeta is in the upper half plane, so the imaginary part is strictly positive, it is non-positive. So it is a function having a holomorphic property, which is mapping the upper half plane into the lower half plane. Okay, if we put a minus, we are getting a function, a holomorphic function, which is mapping the upper half plane into itself. We are making a Cayley transformation. We are bringing the half plane into the disk, and then we can apply the Herglotz theorem. And this is exactly where the Herglotz theorem is coming. Because from that property, we are getting exactly an integral representation with respect to this kernel. The kernel is changed because we are making a Cayley transformation. It's a fractional linear transformation from the upper half plane into the disk. Yeah? And this is a point which is crucial for this theorem. So in the end, I'm just skipping the details. This is what Heinz Langer got. So he couldn't get a spectral measure, but he got a spectral distribution, and the singularities, there are only a finite number of singularities which are exactly the real roots of the definitizing polynomial. Okay, this operator may also have non-real spectrum, but they are only eigenvalues, a finite number of them, and they come in conjugate pairs. So what he obtained was actually a spectral distribution which is of measure type on each interval which is not containing these numbers, a finite number of them, are called critical points. And in the neighborhood of every critical point, the distribution has a finite singularity type. So it is a finite derivative of a delta type function.
But if it does not have real roots?
Sorry?
It's possible if polynomial will not have real roots.
The definitizing polynomial is always supposed to be real, because the thing is the following, and this is my slide. You know, here we are talking about real coefficients P and Q. So what he did exactly was to solve this kind of problems under certain assumptions on the weights R and P. But this is a huge business. So what he did that was for the case of definitizable in this case, but there are more recent and more advanced things in which we have accumulation of singularities at some points. And this gives distribution, spectral distribution that have complicated behavior. But this is a full domain and a full topic. I spent my first 15 years in mathematics working in spectral theory of operator in crime spaces. Thank you so much.